So probably the last time you did probability was in junior high. I can't remember if it's grade 8 math. I think. In any case, so we're reviewing all that work on probability and then talking about a little bit more than you might have back then. So probability measures the likelihood of an occurrence of an event. Probability can be expressed as a fraction, a decimal, or a percent. So really you have to look at what the question is asking. If an event can never happen, then the probability is 0. If an event is certain to happen, then the probability is 1, or 100%. Probability of any other event will fall between 0 and 1. Okay, so this is kind of the notation, capital P. So sometimes we use capital P for a polynomial. But in this case, context is we're dealing with probabilities. So the probability of any event has to be greater than or equal to 0, less than or equal to 1. So some of the terminology. An experiment, that's an action that has measurable or quantifiable results. So the experiment, what you get your results from. Okay? So one experiment is rolling a die and recording the number on the top face, what lands. Outcome, that's the different results possible for one trial of an experiment. So one outcome of rolling a die is 2. For rolling a regular 6 die, there are 6 possible outcomes. 1, 2, 3, 4, 5, 6. Sample space, that's a set of all possible outcomes of a particular experiment. Often we call it U. So the sample space of rolling a die is 1, 2, 3, 4, 5, 6. Each specific one is one of the outcomes. An event, any collection of possible outcomes of an experiment. So rolling a die and getting an even number. Okay, that's the event of the experiment. What you're looking for in that experiment. Frequency of an outcome, the number of times that it occurs. And the relative frequency is the frequency of that outcome expressed as a fraction or percentage of the total number of trials. So really, it's like a probability, although it's representing from an experiment, so it's not the theoretical probability, which we'll talk about here. Okay, so how do we calculate the probability that when a thumbtack is tossed, it will land point up? The only way to calculate this is through experimentation. Okay, so suppose that after 60 tosses of a thumbtack, the tack lands point up 39 times. So we say the probability of the tack landing point up is 39 over 60. Okay, so that's called experimental probability. We did an experiment. We found the likelihood of that to happen. So the experimental probability is really the relative frequency. That's the same. So this is the same as experimental probability. Okay? In cases where all possible outcomes are known and all outcomes are equally likely, then we can calculate a theoretical probability. So if an experiment has n likely outcomes, of which r outcomes are favorable to the event, then the theoretical probability is r out of n. Okay? So n is usually the number of possible outcomes that you could ever have, and r is the number that are possible for that experiment. So one would be like tossing a coin. So probability of flipping a head when you toss a fair coin, so it's not weighted on one side. The experimental probability could be calculated if you do an experiment. You toss a coin 100 times, head shows up 45 times. The probability as a fraction there, experimental probability, would be 45 over 100, which reduces to what, 9/20ths? As a decimal, 0.45, as a percent, 45%. Okay, now, if you did that experiment enough times, so basically approaching an infinite number of times, that experimental probability would approach the theoretical probability. Now, theoretically, when you toss a head, there's a choice. The toss a coin. There's a choice. Could be heads or tails. Two choices. So if it's a fair coin, out of 100 times, you should get heads 50 times, or half, right? Because there's two possibilities. So as a fraction, it would be half. As a decimal, 0.5. As a percent, 50%. That's theoretical. So you can see it's close in this experiment. The more experiments you do, the closer that 45 becomes 50. Okay? So every time an experiment is performed, the results may be different. For instance, if a coin was tossed 100 times one time, you could get 57 heads. Another time, you could get 60. With an experiment, when an experiment is repeated many times, it will approach the theoretical probability, as I just said. Okay? So let's talk about sample spaces for different experiments. So while some sample spaces can be listed easily, sample spaces for experiments that involve more than one operation may be more easily represented with a grid or tree diagram. So, first one, illustrate the possible outcomes for drawing two marbles from a box containing a number of red, green, and yellow by using your two-dimensional grid. And this is sample space. So we don't know how many red, green, and yellow, but we know there are some of each. And we're going to basically draw a grid here with the colors of each marble, so red, green, and yellow. And this would be our first marble drawn, or it could be the second, it doesn't matter. And we'll do red, green, and yellow here. So it doesn't, as long as you label it, it doesn't matter which is which. Okay, so the possible sample space outcomes that you could get if you draw a marble, one marble, and then another one, and there's a number of each of them. We don't know how many, so this is in general. We could have two reds in total. We could have here, first marble is green, second is red. First marble is yellow, second is red. First marble is red, second is green. Both are green. First marble is yellow, second is green. And so we're just basically recording the sample space. What the possible two marbles would look like. We would, in order to calculate probability specifically, we would need to know how many red, green, and yellow we have in order to get the exact probability. But this would be called the sample space. So I'm not going to rewrite it. I'm just going to label it here, sample space. If you listed it, it would just be R, R, G, R, Y, R, R, G, G, etc. Okay. And then at the underneath here, we left a lot of space, but it says what is P, the probability of at least one red marble. Okay. Now, this is just going to be in general because we don't know how many reds, yellows, and greens there are. But based on this, at least one red would be this, 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 and this. Oh, sorry, and this one. Okay, so 5 out of the 5 of those cases out of the 9. So in general, it would be 5 ninths. Okay. Yep. It depends on the question. If you're choosing them one at a time, then you and then you're asked for just in that pair how many are red, then you look at both cases. Yeah. Okay, so a tree diagram, that's what I often use. I don't use the grid that much. So illustrate on a tree diagram the outcomes for tossing a four-sided die and 2 coins. So a four-sided die would be what we call, phones away, a tetrahedron, okay, in science. So that's like a triangular-based pyramid. It's got 4 sides. So that would be what this die looks like. One four-sided die. So your choices are 1, a 2, a 3, or a 4. So that's for your die. I think die is singular for dice. Okay, and then 2 coins. So the first one, okay, would be heads. Actually, I would do it a little bit shorter because we have 2 of them. So heads or tails, heads or tails, heads, tails, heads, tails. Okay, and then for each of those, the next coin, so this is a coin, and then another coin. Heads or tails, heads or tails. Got to kind of squish it in down here a little bit. Okay, so your sample space is each arm of that. So for example, it would be, the first arm would be 1 and then 2 heads. The second one would be 1 and then heads and then tails. Then 1 and then tails and then heads, etc. I'm not going to copy it all out. It's each branch of that chart. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Basically, you can get that. There's 4 possible outcomes for the die. 2 possible for the first coin, 2 possible for the second, so that's 16 possible outcomes. Okay. So what is the probability of tossing an even number, or rolling an even number, and 1 head and 1 tail? Okay, so even number is 2 and 4, right? And 1 head and 1 tail. So that would be this arm here. A little bit slow. And then this one underneath. Okay, so those 2. And then another even number here. 1 head, 1 tail. And then 1 tail, 1 head. Okay, so that's 4. Here, so that's 4 out of 16, which is 1/4. So, next definition to look at here is the complement of an event. So the complement of event A is the event that A does not occur. So it's sort of everything that's not A. And so we use a prime symbol, like an apostrophe, or a bar over top. Usually it's that prime symbol. So example, a die is rolled, if A is the event of rolling a 5, then A prime is the event of rolling a 1, 2, 3, 4, or 6. Everything in the sample space that is not 5. So, probability of event A is 1/6. Probability of the complement is 5/6. Okay, it's 1 minus this. So when you basically here, you're adding the probability of the event A and its complement, you always get 1. Okay, so you can always get the probability of the complement by subtracting from 1. So if the probability of winning a particular game is 0.26, then the probability of not winning is 1 minus 0.26. So that's 0.74. And then, turn over the page, mutually exclusive events. What does that mean? So, mutually exclusive events are 2 or more events. So this is, you can only use this wording if you have 2 or more events happening. So those 2 events or more are mutually exclusive if they cannot occur at the same time. So they have no common outcomes, okay, that you could sort of overlap with each other. So for example, you've got a 6-sided die, it's rolled. The probability of rolling a 1 is 1/6. Probability of rolling a 3 is 1/6. Okay, probability of rolling a 1 or a 3, well, that's 2 possible out of the 6, which is 1/3. So rolling a 1 is mutually exclusive of rolling a 3. You cannot get a 1 and a 3 in one roll of that die. There's no 1/3 on a die, right? So rolling it once, you can only get either the number 1, or the 2, or the 3, all the way up to 6. You cannot get both of those things at the same time. So they're called mutually exclusive events. And to get the probability of rolling a 1 or a 3, you can add the probabilities together. Okay? So if A and B are mutually exclusive, and you're asked to find the probability that A or B occurs, you can just add the separate probabilities together. Remember that OR is the same as the union. And so tomorrow we'll talk about Venn diagrams. We talked about them at the beginning of the semester. Now we're going to talk about Venn diagrams in terms of probability, and it will be the same thing. So mutually exclusive in a Venn diagram, the circles will not overlap. Okay, those are mutually exclusive. If they overlap, then they're non-mutually exclusive because they would have events in that overlap that could happen at the same time. Okay, and that would be an example coming up here. So a card is randomly selected from a standard deck. Probability of a queen or an ace. So that's mutually exclusive. You can't draw a queen and an ace at the same time, right? That's like the number on the card. So probability of a queen plus the probability of the ace will give you the total. So queen, there are 4 out of 52 in a deck. Ace, there are 4 out of 52. Okay, so that's going to be 8 out of 52. And that reduces to what? 2 over 13. Makes sense. Within each suit, there's 1 queen and 1 ace. Right? So 2 out of the 13 in a suit. And that's how it reduces. Okay? So you can't have a queen and an ace at the same time. But what about having a queen and a heart? Sure can, right? The queen of hearts, because the heart is the actual suit of the card. It's not a number of the card. Okay, so non-mutually exclusive events, Those are two or more events that have common outcomes. And so an example here, we know the probability of a queen is 4 out of 52. Probability of a heart, well, there's 13 hearts out of 52. Okay, that reduces. I'm just going to keep it out of the 52 for right now. And so probability of a queen and a heart, well, there's only one queen of hearts in a deck. So 1 out of 52. Okay. Probability of a queen or a heart, well, let's think about that. Queens, there's 4. Hearts, there's 13. But one of them is the queen of hearts. So I've already counted. So this is 4 plus 13 minus 1. Right? So it's really 16 out of 52. And that can reduce if you want to reduce that. That goes over 4, 13. If you want to reduce them, you can. Okay. So drawing a queen and drawing a heart are not mutually exclusive because drawing a queen of hearts is a common outcome. So take a look. Queen or a heart, oops, I said was 16 out of 52. Probability of a queen was 4 out of 52. Heart was 13 out of 52. Notice how that adds to 17 out of 52. It is not equal to 16 out of 52. Okay? So, what's happened here, we have to subtract the queen of hearts, right? The one that's the and. So, what relationship is true? We have to go probability of queen or heart equals probability of queen plus probability of heart minus the probability of the queen intersect the heart. Okay? Because we've already counted it. So that is like a Venn diagram question from the beginning of the semester. Right? So in this, we have 4. But one of them is a queen of hearts, so there's 3 there. 13 hearts, one of them is a queen of hearts, so there's 12 there. Okay, yep.
So would the order in this case be like XOR, so like one or the other, but not both?
No, or means one or the other or both. Or is the hub. It's everything in all of it. Okay. So that's why here, A or B is going to be 16, not 17, right? Because you can't count something more than once. So this can't be counted separately as a queen and separately as a heart, because it is the queen of hearts. Okay. So we talked about this sort of in numbers, in Venn diagrams, but not with probabilities. It's the same thing though. Okay. You actually did questions like this back in the reasoning unit. Okay, so note that if A and B are mutually exclusive events, then you can still use this formula. There's just not going to be anything that intersects, right? So you can still use it. It's just these two added together. But if they are not mutually exclusive, then you have to take that into account. Okay, and so that's where we're going to end for today.